DOF parallel grippers are easy to control but limited to simple grasping tasks, lacking the ability to perform in-hand manipulation. On the other end, high DOF dexterous robotic hands, such as the 16 DOF Allegro hand, has high versatility but requires comprehensive control methods. The potential for in-hand manipulation with lower DOF grippers remains underexplored. Therefore, in this paper, we introduce a gripper design powered by a visual tactile sensor, capable of performing dexterous tasks with only 5 degrees of freedom. Previous studies on two-finger tactile grippers with multiple DOF face several limitations, including the need for specialized tactile sensors and reduced suitability for general-purpose tasks or delicate manipulations due to their round finger design. The proposed gripper features 2 fingers, each consisting of a linear actuator and a rotational servo motor. The fingers are attached to the parallel Weiss WSG32 gripper, with all components 3D printed using PLA material. The left fingertip is equipped with a GelSight mini tactile sensor, while the right fingertip is fitted with a silicone fingernail, rated at 60 Shura hardness. The first task is in-hand singulation. We use a tactile MPC controller to maintain robust grasping and a linear controller to regulate the range of the rubbing motion. After the initial grasp, rice stuck between the object and the finger makes classification difficult. However, once singulation is complete, the object's features become clearly. We evaluate a total of 10 objects with varying sizes, surface textures, geometric shapes, and physical properties. This video shows a failure case of singulating a peanut, where the object slips due to a sudden change in the gripping width as rice particles fall. We achieved an overall success rate of 84% for all objects, specifically, a notably high rate of 93.3% for sphere objects. The second task is in-hand scooping manipulation and insertion. Using the design maneuver based on 5 DOF, our method achieved a 100% success rate for the complete task, including in-hand scooping, reorientation, and insertion, with the credit card placed in random initial poses. The third task is cable untangling. We propose a sampling-based tactile exploration method that uses a single tactile sensor to identify the untangling point without altering the cable state, in contrast to our previous cable following method. With 2 maneuvers designed using the 5 DOF, our gripper can effectively untangle 2 entangled cables in various situations. We also evaluated the generalization ability of our gripper and methods on 5 additional entangled cables with varying materials and diameters, set to untangle 1 knot per attempt. The results demonstrated that our method performs well across different cable types. We compared our method with 2 benchmark approaches. The first relies solely on vision, using an external camera to estimate the cable state. However, without precise tactile perception, millimeter-level errors can cause the fingernail insertion to fail, leading to unsuccessful cable untangling. Next, we compared the vision tactile method. While this approach significantly improves untangling efficiency, its major drawback is the reliance on a clear background for accurate semantic segmentation, unlike the tactile-only method. In cluttered environments, this limitation hinders successful cable untangling. The results showed that the proposed tactile-only cable untangling method using the 5 DOF gripper achieved the highest success rate compared to the 2 benchmark methods. However, its efficiency was lower, presenting a trade-off between success rate and speed. Finally, we extended our method to the task of 3 cable untangling in a special case, achieving an overall success rate of 60%. To handle more complex scenarios, a promising future direction would be to explore the use of 2 tactile sensors to perceive the state of the cables in 3D space, more closely mimicking human dexterity.